Welcome to the Deep Dive. We take fascinating sources, pull out the key insights, and get you informed fast. Today, we're tackling something huge. Science. I mean, we rely on it constantly, right? Our phones, medicine, understanding the universe. We trust the facts it gives us. But have you ever really stopped to think, what is science? How does it actually work? And does it have limits? So our mission today is a shortcut, really, into the philosophy of science. We're diving deep into a brilliant, very short introduction that questions the assumptions scientists often just take for granted. Get ready for some, properly mind-bending stuff, some surprising ideas, and maybe those aha moments that shift how you see, well, pretty much everything, from your laptop booting up to reality itself. Okay, so let's jump in. What is science? Really, what makes it tick?
That's the perfect place to start, because it's something we, rarely question. We talk about the scientific method, but if you look closely, you see core things. Observation, careful experiments, trying to build general theories that explain what we find. And a big part of philosophy of science is analyzing those methods, yes, but also questioning the bedrock assumptions scientists might not even realize they're making.
Assumptions like what? Give me an example.
Well, okay, say a scientist runs an experiment 5 times, gets the same result each time. They might confidently say, okay, done, assuming the 6th, 7th, 100th time will be the same. Philosophy asks, why? Why assume that? How do we know nature will keep behaving that way?
Right. The working scientist probably doesn't pause for that. But it's fundamental, and it leads straight to this other huge challenge, telling real science apart from, well, stuff that looks like science but isn't. Pseudoscience, the demarcation problem, they call it. And Karl Popper, a really major philosopher here, had a famous answer. He said, scientific theories must be falsifiable.
Yeah, falsifiable.
What does that mean exactly? Falsifiable.
It doesn't mean the theory is wrong. It means it makes specific, definite predictions about the world. Predictions that you could, in principle, test and find to be wrong. If your theory can wiggle out of any potential counter-evidence, if it's compatible with everything that could possibly happen, Popper thought, well, that's not science. It's too slippery.
So theories need to stick their necks out, basically, take a risk.
Precisely.
And what examples did he use for pseudoscience, stuff that wasn't falsifiable?
He often pointed to Freud's psychoanalysis and Marx's theory of history.
Yeah.
With Freud, Popper argued, concepts like repression or sublimation could explain literally any human behavior after the fact. Whether someone acts heroically or despicably, a Freudian explanation could be found. It could never be proven wrong.
Okay.
And similarly with Marx, when communist revolutions didn't happen as predicted in advanced capitalist societies, Marxists didn't abandon the theory. They came up with, ad hoc reasons like the welfare state temporarily placating workers. For Popper, this constant explaining away made them unfalsifiable, pseudoscientific. They could never lose.
But then he held up Einstein's theory of gravity, general relativity, as the gold standard. Why Einstein?
He was hugely impressed because Einstein made this incredibly bold, precise prediction that starlight passing near the sun would be bent by its gravity, a very specific amount. You could only test it during a solar eclipse. And in 1919, Arthur Eddington led expeditions that did just that. And bang, the starlight was deflected, almost exactly as Einstein predicted.
Wow.
If the measurement had been different, the theory would have been falsified. It took a real gamble. That, for Popper, was proper science.
Okay, so Popper gives us this neat dividing line. Science is falsifiable. Seems clear enough, but is it really that simple when you look at how scientists actually do science?
Yeah, that's where it gets tricky. Popper's idea sounds good, right? Who wants a theory that explains everything and nothing? But many critics say it's just too simple. If you look at the history of science, scientists don't usually ditch their theories the moment some data doesn't fit. Think about Uranus's orbit back in the 19th century.
Right, it wasn't quite following Newton's predictions.
Exactly. But did they throw out Newton's laws? No. 2 scientists, Adams and Leverrier, independently thought, maybe there's another planet out there pulling on Uranus. They calculated where it should be based on Newton's laws. And bingo, they discovered Neptune.
So the anomaly, the conflicting data, actually led to a new discovery within the existing framework. They didn't falsify Newton.
Precisely. And the thing is, almost all major scientific theories have some observations that don't quite fit, especially early on. If scientists followed Popper strictly, they'd abandon potentially great theories too soon. This leads to a different idea, maybe from Wittgenstein, the philosopher. He talked about family resemblance. Like games, there's no single thing all games have in common, just overlapping similarities.
So maybe science is like that. Not one strict definition, but a cluster of related features.
Could be. It makes drawing that sharp line Popper wanted much harder.
Okay, so defining science is complicated. What about how scientists actually reason? How do they get from observations to these big theories? Philosophers talk about deduction and induction. Can you unpack those?
Sure. Deduction is the watertight one. If your starting points, your premises are true, then your conclusion must be true. Think math proofs, like premise 1, all humans are mortal. Premise 2, Socrates is human. Conclusion, therefore Socrates is mortal. If 1 and 2 are true, 3 has to be. No wiggle room.
Got it. Solid logic. But induction is different, more common in science, maybe.
Much more common. Induction is where your premises make the conclusion likely or probable, but not absolutely certain. You're moving from cases you have observed to cases you haven't. Like, you pull 5 black socks from a drawer, you reason inductively that the next sock you pull will also be black. Seems reasonable, right?
Yeah, makes sense.
But it's not guaranteed. The next one could be white.
And we do this all the time without thinking. Like, you expect your chair to hold you because it always has. You turn the key in your car expecting the engine to start. That's induction.
Absolutely. And science is built on it. Think about genetics. How do scientists know all people with Down syndrome have 47 chromosomes?
They test a lot of people with Down syndrome.
Exactly. They test a large sample, find the extra chromosome consistently, and then infer inductively that it holds true for all cases, even the ones they haven't tested.
Or Newton's law of gravity. He didn't test every object in the universe.
Not even close. He observed planets, apples falling, stuff like that, saw a pattern described by his law, and inferred it applied universally to all bodies. That's a huge inductive leap.
So we hear about scientific proof all the time, but based on this, it sounds like it's usually not proof in that strict deductive mathematical sense.
Rarely, if ever. Scientific evidence can be incredibly strong, overwhelming even, but it's typically built on inductive reasoning, which leads us to a really unsettling idea from the philosopher David Hume.
Hume's problem of induction.
That's the one. Hume basically argued, way back in the 18th century, that using induction isn't actually rational. We do it constantly, but he said it's just habit, animal instinct, blind faith.
Whoa, so believing the sun will rise tomorrow because it always has, that's not rational, that feels wrong. How did he argue that?
It's powerful stuff. He said induction always relies on a hidden assumption that the future will resemble the past. He called this the principle of the uniformity of nature, or UN for short. We assume the laws of physics won't suddenly change overnight. But Hume asked, how do we know UN is true? Can we prove it?
Okay, can we prove it deductively, like a math proof?
Hume says no, because we could easily imagine a universe that's not uniform, where gravity suddenly stops working tomorrow. Since a non-uniform universe is conceivable, we can't logically prove nature must be uniform. Deduction fails.
All right, so no deductive proof. What about using induction itself? Like, hey, nature has always been uniform up to now, so it probably will continue to be.
But that's the killer move from Hume. He says that's circular reasoning. You're using induction, reasoning from past uniformity to future uniformity, to justify induction.
You're assuming the very thing you're trying to prove.
Exactly. Begs the question. You can't use induction to convince someone who doubts induction in the first place.
Wow. So if Hume's right, the entire foundation of science, all this knowledge we build about the world, rests on an assumption we can't rationally justify. Just faith that the universe won't suddenly go haywire.
That's the unsettling conclusion. It suggests our confidence in science is, at bottom, a kind of habit or trust, not strict logical proof.
That really makes you rethink things. What does scientific proof even mean then? It's more like overwhelming evidence based on this shared faith in uniformity.
It's had a huge impact. Philosophers have tried to respond, of course. Some talk about probability induction makes conclusions highly probable, even if not certain. But defining probability gets complicated too. Others, like Peter Strawson, argued that induction is just fundamental to what we mean by rational justification. Asking if induction itself is justified is like asking if the law is legal. It doesn't make sense. It is the standard.
Interesting. So maybe it's just part of the definition of reasoning about the world. Okay, moving beyond simple induction. Scientists don't just predict, they explain. There's another kind of reasoning here. Inference to the best explanation, or IBE. What's that about?
IBE is super common, both in science and everyday life. It's about choosing the hypothesis that provides the most plausible explanation for your evidence. Like, you come home, the cookie jar is empty, there are crumbs on the counter, and your kid has chocolate on their face.
I infer the kid ate the cookies.
Right. That's the best explanation. You could invent a story about, I don't know, a very specific cookie-stealing burglar, but the kid hypothesis is simpler, more likely, fits the facts better. That's IBE.
Makes sense. And this ties into how science explains things. Carl Hempel had a famous model for scientific explanation, the covering law model. What was his idea?
Hempel thought explaining something meant showing how it logically follows, deductively, from general laws plus some specific facts. His classic example. Why did this specific plant die? Well, law. All plants need sunlight. Fact. This plant was kept in a dark cupboard. Conclusion. Therefore, this plant died. The explanation shows the event was expected given the laws and facts.
Seems logical. Why did the plant die? Because it needed light and didn't get it. Covered by a law.
Exactly. It has intuitive appeal. But it runs into some pretty big problems.
Like the flagpole.
Like the famous flagpole problem. Okay, so the height of a flagpole, the position of the sun, and the laws of optics. You can deduce the length of the shadow it casts. That fits Hempel's model. The shadow length is explained.
Right, height plus sun angle plus laws shadow length.
But now flip it. The shadow length, the sun's position, and the laws. You can deduce the flagpole's height. Hempel's model says you've now explained the flagpole's height.
But that feels wrong. The shadow doesn't cause the flagpole's height. The flagpole's height causes the shadow.
Precisely. Explanation seems to be asymmetric causes explain effects, not usually the other way around. Hempel's deductive model misses this asymmetry. It treats both calculations the same.
And there was another problem? Something about irrelevance.
Yeah, the problem of irrelevance. Imagine someone asks why, say, John Jones, a man, hasn't become pregnant. According to Hempel, you could offer this. Law. Men who take birth control pills regularly never become pregnant. Fact. John Jones takes his wife's birth control pills regularly. Fact. John Jones is a man. Conclusion. Therefore, John Jones hasn't become pregnant.
Okay. That technically fits the structure. Law, facts, deduction.
But it's obviously a ridiculous explanation. The pills are irrelevant. John hasn't become pregnant because he's male.
Right. The model doesn't filter out irrelevant information.
And what both these problems point to is that Hempel's model missed something crucial. Causality. Often, a good scientific explanation involves identifying the cause of whatever we're explaining. Hempel tried to avoid causality because it seemed philosophically fishy to empiricists at the time. But it turns out explanation is often deeply tied to it.
So Hempel's model was too simple. It missed the direction of explanation and the importance of causes. This brings us to the limits of science. We know science hasn't explained everything yet, like exactly how life originated or why some autistic kids have these incredible specific memory skills. But are there things science might never be able to explain, in principle?
That's a deep philosophical question. One argument is that science explains things using more fundamental laws or principles. But what explains the most fundamental laws, like why is gravity the way it is? If they're truly fundamental, then by definition, there's nothing more basic to explain them. So you hit a bedrock of brute fact. Nothing explains itself.
Okay, so maybe the ultimate laws are unexplainable. What about more specific things? Consciousness comes up a lot here.
Yes, consciousness. Especially the subjective first-person experience, the what it's like to see red, or taste coffee, or feel pain. Philosophers call this qualia.
Can brain science, neuroscience, ever fully explain that feeling? Not just the brain activity associated with it, but the feeling itself.
That's the huge debate. Many philosophers argue no. They say science describes objective, physical processes, neurons firing, chemicals releasing, but subjective experience seems fundamentally different, non-physical somehow. How do you get subjective what it's likeness from purely objective physical stuff? It's called the hard problem of consciousness.
Like trying to explain the experience of music just by analyzing sound waves.
Kind of. It feels like something essential is left out. But it's crucial to say this is hotly contested. Philosophers like Daniel Dennett argue forcefully that consciousness can be explained scientifically, perhaps by showing the subjective aspect as a kind of complex illusion generated by the brain. And, history warns us against saying science can't explain something. Many things once thought inexplicable are now understood.
True. Okay, let's shift gears slightly. What about the status of scientific knowledge itself? When theories talk about things we can't see, atoms, electrons, genes, should we believe those things actually exist? Is the theory a true description of reality? This is the realism versus anti-realism debate, right?
Exactly. Scientific realists say yes. Our best, most successful scientific theories, think atomic theory, genetics, they argue these theories are at least approximately true descriptions of the world, including the unobservable bits. Their big argument is often called the no miracles argument. It would be an absolute miracle, they say, if theories that work so well making incredibly accurate predictions leading to new technologies weren't actually latching onto the real structure of the world. Success like that can't just be luck.
Okay, so success implies truth. But the anti-realists or instrumentalists disagree.
They take a more cautious, maybe skeptical stance. They say, look, scientific knowledge is really solid when it comes to the observable world. The things we can see, measure directly, like fossils, planets moving, chemical reactions in a test tube. But when theories talk about unobservable things like electrons or quarks, anti-realists view these as useful tools, convenient fictions maybe. They help us predict and organize observable phenomena, but we shouldn't necessarily believe they literally exist or that the theory is a true picture of that hidden reality. The theories are instruments, not mirrors.
And they have a counter-argument to no miracles.
They do, a powerful one. The pessimistic meta-induction from the history of science. They point out that history is just full of theories that were incredibly successful in their day, made great predictions, were widely believed, and turned out to be wrong.
Examples.
Well, the phlogiston theory of combustion was successful for a while. Or, a really big one, the 19th century physics belief in the luminiferous ether, a medium that light waves supposedly travel through. It explained a lot, led to predictions. But we now know there's no ether.
So, if past successful theories turned out to be false, why should we be so confident that our current successful theories about electrons, dark matter, etc. are true? Maybe they're just the next successful but ultimately wrong theories.
That's the pessimistic induction. It really challenges the realist's confidence based purely on success.
And this whole debate seems to hinge on being able to clearly distinguish between what's observable and what's unobservable. But is that distinction actually clear-cut?
That's a major problem for the anti-realist position. It needs that distinction to work. Knowledge is reliable for observables, but just useful fiction for unobservables. But drawing the line is really hard. The philosopher Grover Maxwell made this point brilliantly. Think about it. Seeing something with the naked eye clearly observable. What about looking through a window? Through glasses, through binoculars, through a simple microscope, through a powerful electron microscope?
It feels like a smooth continuum.
Exactly. Where do you draw the line and say, okay, now it's unobservable? Is seeing the vapor trail of an electron in a cloud chamber observing the electron, or just detecting its effects? Scientists themselves often talk about observing particles using complex detectors.
Yeah, they wouldn't necessarily make that sharp philosopher's distinction between observing and detecting. It blurs the line anti-realism seems to rely on.
It really does. If you can't make a clear distinction, the whole anti-realist idea of limiting belief to the observable starts to look shaky.
Okay, thinking about how science changes over time. Thomas Kuhn's work here was completely revolutionary, wasn't it? He challenged that simple idea of science just steadily accumulating facts, progressing towards truth.
Hugely influential. Kuhn talked about normal science. That's when most scientists work within a shared framework, a set of assumptions, methods, and core theories he called a paradigm. Think Newtonian physics for a couple of centuries. Doing normal science, scientists aren't usually trying to overturn the paradigm. They're solving puzzles within it, refining it, extending its reach.
Like filling in the map, not drawing a new one.
Good analogy.
Yeah.
But, Kuhn said, over time, anomalies pop up results that just don't fit the paradigm, no matter how hard scientists try to make them fit. If enough serious anomalies accumulate, it leads to a crisis.
And the crisis leads to
a scientific revolution. Eventually, a new paradigm emerges, offering a radically different way of seeing the world that can explain the anomalies, and hopefully most of the old stuff too. Think Copernicus replacing Ptolemy's Earth-centered universe, or Einstein replacing Newton for gravity and motion at high speeds.
And Kuhn's really radical claims were about what happens during these revolutions, right? This idea of incommensurability.
Yes, incommensurability. He argued that the old and new paradigms are so different, they use key terms differently, they focus on different problems, they even have different standards for what counts as a good explanation, that proponents of the competing paradigms almost literally talk past each other. They can't find enough common ground for a purely rational, objective comparison to decide which one is better or truer. This implies scientific change isn't necessarily a linear march towards the truth, but maybe more like shifts between different, potentially incompatible ways of seeing the world.
So not climbing the same mountain higher and higher, but maybe switching mountains entirely?
Something like that. And tied to this was his idea of the theory-ladenness of data. Kuhn argued that what scientists even perceive as data or facts is influenced by the paradigm they accept. There's no perfectly neutral observation language to compare paradigms objectively.
That sounds like it really undermines the traditional picture of science as purely objective, if even the data isn't neutral.
It was a huge challenge to that picture. But it's important to stress, Kuhn didn't see himself as anti-science. He was trying to give a more historically accurate account of how science actually develops, warts and all. He thought its power didn't rely on the simple, idealized view.
It's a much more complex human picture of science.
Absolutely. And these ideas connect nicely to practical issues like how we classify things. Biological classification taxonomy is a great example.
We learn the Linnean system in school kingdom, phylum, class, order, etc. But there are big debates in biology now about the right way to classify, aren't there? Between phoneticists and cladists?
Yes, a major ongoing debate. Phoneticists basically classify organisms based on overall similarity, morphology, genetics, whatever features seem relevant. You group things that look alike. Cladists, on the other hand, insist that classification must strictly reflect evolutionary history phylogeny. They only recognize monophyletic groups, meaning a group that includes a common ancestor and all of its descendants, nothing more, nothing less.
How does that play out in practice? Give me an example.
The classic one is reptiles and birds. Traditionally, Reptilia is a class, and Aves birds is a separate class. Makes sense based on overall similarity, right? Lizards and birds look pretty different.
Yeah, this seems obvious.
But cladists say no. Birds evolved from dinosaurs, which are reptiles. So to make Reptilia a true monophyletic group, an ancestor and all descendants, you must include birds within Reptilia. Otherwise, you've arbitrarily excluded some descendants of that common reptilian ancestor.
So, cladistically speaking, birds are reptiles. That definitely clashes with common sense.
It does. Cladists argue their way is more objective because it's based on the single true evolutionary tree, even if we don't know it perfectly, not subjective judgments about which similarities matter most. But phoneticists counter that we often don't know the evolutionary history perfectly, so classification should be based on observable similarities first. Cladism makes classification dependent on or laden with evolutionary theory, which phoneticists might see as putting the cart before the horse. It's a fascinating clash about the very purpose and basis of classification.
Okay, as we head towards wrapping up, let's touch on some broader issues about science's role in society. Science has incredible prestige today. Calling something scientific gives it authority. But this can lead to scientism. What's that?
Scientism is essentially the view that science, and only science, holds the key to all genuine knowledge and can answer all meaningful questions. It's an overreach, basically. Most philosophers would argue that there are whole domains of human concern, ethics, morality, aesthetics, questions about meaning and value that aren't really scientific questions and aren't solvable using scientific methods alone. Science can tell us how the world is, maybe predict consequences of actions, but not what's right or wrong, beautiful or ugly, or what makes for a good life.
So science is powerful, but it has its domain. It's not the only path to understanding.
Exactly. Trying to make everything fit a scientific mold can distort those other areas. There's also a related debate in the social sciences. Should sociology or economics try to mimic the methods of physics to be more scientific? That's another complex issue wrapped up in scientism.
And then there's the often fraught relationship between science and religion. Historically, think Galileo. But more recently, especially in the US, it's Darwinism versus creationism.
Yes, that's been a major flashpoint. It pits a literal interpretation of religious texts about creation against the scientific theory of evolution by natural selection. The creation science movement specifically tries to present biblical creation as a rival scientific theory, demanding it gets equal time in science classrooms. This is largely seen as a tactic to get religious doctrine taught in public schools, circumventing the separation of church and state.
And they often use the line, evolution is just a theory, trying to imply it's uncertain, just a guess. So creationism is equally valid as another theory.
Right, which, as we discussed, misunderstands what theory means in science. A well-supported explanation, not just a hunch. The overwhelming scientific consensus finds no scientific merit in creation science. It's seen as religiously motivated, not scientifically grounded.
But it raises real public policy questions about education, who controls curricula, parental rights. It's not just an abstract debate.
Absolutely not.
Finally, one last big one. Is science value-free? Is it purely objective, just discovering facts about the world? Or do values play a role? The common idea is knowledge is neutral. It's how we use it, like nuclear physics for bombs or energy that involves ethics.
That's the traditional view. Science discovers, society applies. But many philosophers argue values are embedded within science itself. For one, scientists have to choose what to study. Funding decisions, research priorities, these involve value judgments about what's important or worth knowing. Also, as we saw with Kuhn, sometimes the data doesn't definitively point to one theory over another. In those cases, non-scientific values, maybe simplicity, elegance, or even social or political leanings might subtly influence which theory a scientist favors.
Can you give an example where values and science seem intertwined?
Human sociobiology is often cited. It tries to explain human social behaviors using evolutionary Darwinian principles.
Like incest avoidance. How would sociobiology explain that?
The argument might be that throughout evolutionary history, individuals with a genetic predisposition to avoid incest produced healthier offspring, fewer genetic defects, on average. Therefore, natural selection favored genes promoting incest avoidance, making it a near-universal human trait. It's an adaptation.
Okay, but that feels different from saying we avoid incest because we learn it's wrong or because of cultural taboos.
Exactly. It creates tension. Sociobiology offers adaptationist explanations for other controversial behaviors too, things like aggression, xenophobia, maybe even rape or differences in promiscuity between sexes. These explanations often clash with cultural or learning-based explanations and can feel uncomfortable, sometimes seeming to justify or naturalize problematic behaviors. It highlights how scientific explanations of human nature are rarely completely separate from our values and social concerns.
It's incredibly complex. So we've really journeyed through the philosophy of science today, from what science even is, how it reasons with tools like induction that have shaky philosophical ground, to whether its theories truly describe reality, how it changes through revolutions, and its complex relationship with values and society. It shows science isn't just a simple fact-finding machine. It's this incredibly powerful, but also deeply human enterprise built on fascinating, often invisible, philosophical foundations. So here's a final thought to leave you with. If our best scientific theories might not be fully determined by the evidence, and if the bedrock of scientific reasoning, induction, rests on an unprovable assumption about nature's uniformity, how certain can you really be about what science tells us? How does that shape your own confidence in what you believe is true?
And in a world so shaped by science, how do we decide as individuals and as a society where the line is between objective scientific findings and the values that inevitably influence its practice and application?
Keep asking those deeper questions. Understanding the philosophy behind the science makes the pursuit of knowledge itself so much richer.